Okay, let's look a little bit more at the difference between uh, regression and correlation analysis and some of the quantifications we can do on these things. So what is the difference between a correlation? Basically, they're sort of the same thing, and you can sometimes use one versus the other interchangeably. The big difference is sort of the perspective you have. Uh, so when you do simply a correlation analysis, you don't know if the two variables really have a cause and effect relationship. Whereas when you use a regression analysis, your assumption is that there is a cause and effect relationship. Doesn't mean that you're demonstrating that there's a cause and effect. It's sort of the perspective you have. So let's say you measure the temperature outside and how sunny it is, and you record uh, the the number of ice cream sold and the amount of sunburn people get. Well, if you plot the ice cream sales versus the amount of sunburn, you might see a correlation, right? They're actually both caused by something else, by the heat, but they're not. One is not causing the other here, right? And so you might want to do this correlation analysis, saying, well, there is a correlation, but you don't suspect any kind of cause and effect. Now, you might record the heat and plot the ice cream sale, and you might say, well, I suspect that the hotter it is, the more ice cream are sold. You don't demonstrate that. It's not a proof of cause and effect, but it's sort of implicit that this is your perspective. Okay. So really using one versus the other is a question of perspective. And if you show a regression, you're sort of implying a cause and effect relationship. So if you don't think there's a cause and effect relationship, or you don't want to imply that, then you use a correlation. And what's the big difference in terms of quantification? Well, a correlation is quantified with a correlation coefficient called R, and um, for a regression, you use a coefficient of determination that we usually call just the R square, right? What's the relationship between this R and this R square? Well, R is the square root of R square. So it's the same R basically. You square it to get the R square that you use for regression, but you see that they're basically the same thing. And so the two analyses are fundamentally the same. It's just a question of perspective. Okay, we've been talking about R and R squares a lot, but this class so far, we've been looking at p-values, statistical analysis, and the R square is not it. The R square doesn't tell you how sure you are that there is a correlation or that there is a regression, a, 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 a positive regression or a significant regression between the two. And actually, when you run a regression analysis in Excel, you will get both an R square and a p-value. And so what's the difference? Well, we explained that the R square explains or indicates how variable the data is around your trend or how much noise there is. And you have an example here. This data set here all falls in line. You have a very high R square. And the more noise I put into this data set, the smaller the R square. So here the R square is below 0.1 because you have a lot of noise around your line. Now, this will also to some degree affect the p-value, but what does the p-value tell you? The p-value, you see, even here, it's, well, here it might be, depending on what threshold you use, 0.04. So if you take 0.05 as a threshold, it might still be significant. This tells you whether this slope, the slope of the relationship, so this A for y equals ax plus b, so the slope, is it significantly different from 0? If it's not significantly different from 0, you don't know. It could be y equals 0x plus b. So 0x means that you take out x out of the equation completely, and y equals b, right? So it would be basically a flat line here, and knowing x will not help you at all to know y because they're not correlated. There is no significant regression between the two. Okay, so let's take this data set here. I plot it here. Another thing that can affect your p-value is the number of samples you have. So I took the same data set, but here I took randomly only 40 data points, and here 10 data points. And you can see that overall the R-square stays more or less the same. And the estimate will vary a little bit because it's not exactly the same number of data points, right? But the variability around the line stays more or less the same because it's the same data set. And the slope stays more or less the same, but the p-value, you can see here, the p-value is very small, 0.0001, here 0.001, and here 0.60. So here it's not significant anymore. I don't have enough data points to be sure that this slope is significantly different from 0. Okay. Another thing that will obviously affect this p-value is how big this slope is, right? So if I keep the same, again, I use this middle data set here and put it here, I keep the noise, the same strength, but I change the slope. So the closer the slope is to 0, the harder it is going to be to determine that it's not 0, right? So here, the slope is, it's around 10 here, the estimate at least, and you can see that the p-value is significant, 0.001. Here I change the slope, 0.86, and the p-value is starting to be higher. And here the slope is even smaller, and the p-value is not significant. Okay, that affects also the R-square because the slope changes relative to the size of the noise. So this R-square, also there's a relationship between the strength of the relationship, so the slope, and the amount of noise. So here I kept the slope fixed, and so that's why we see R-square changing, but keeping the noise fixed and changing the slope, you have a similar effect on the R-square. So all these things are things that affect the R-square and the p-value, and you see how they explain things different, right? The R-square is the amount of noise, whereas the p-value tells you whether the relationship is significantly different from 0. Okay, make sure you understand these two concepts, and I have just a few more tips on like how to design good experiments using regression analysis.